everyone in Mathland. We are getting into lesson 22, Michelle Obama and I. Also, in addition to our special guest, Michelle Obama, we have, for the first time this school year, very special mathematicians that are going to be doing these these problems with you. Our first guest mathematician is Kira. Kira, do you want to say hello?
Hi.
And Melon, you want to say hi?
Hi.
Beautiful. Come over here. And Melon and Kira are going to share our learning target for today in your own words. What are we doing today in your own words? Try to use a big voice.
So basically, we are comparing the size of the answer that we get to a multiplication project.
Cool. So we're comparing the size. It's kind of loud in here. I'm just going to rephrase that. We're comparing the size of the product.
See, can I work on my desk?
I honestly to the size of the factor. Anything else we need to know before we get into these problems? No, go to the front table, please. I'll be right with you.
That's good.
Okay, are you guys ready?
Yeah.
Are you guys ready?
Yes.
Let's do this! Okay, buddies. So, before we get into our guest teacher's problems, your old boring teacher's going to do some problems. So, one of the kind of key words in this lesson is scale, and I want you to consider what scale means. Scale, for instance, say I've started this amazing putty company, and it's, actually I just thought of like the best name for a putty company. Say it's called, hold on, I need this to be bigger. Okay, so my putty company is going to be called MC Putty. Ha! That's actually a brilliant idea, because those are my initials. So MC Putty, and I'm just like selling my putty. I'm not doing this for real. This is just an example. But if I were to do this, I'm selling my putty, say, for $1 to kids in my class, which I don't think is legal. So I'm not doing this for real. I'm just making up a problem. So I'm selling this putty for $1 just to kids in my class. And, maybe I made $26 today because there's 26 kids in my class. And then word is getting out that, like, your putty is amazing. So now I'm starting to do business with my whole school. So maybe, like, in a day, I'm making double what I did just for my class. Or then, like, word's spreading. And then another day, I'm, like, making double that. So as word spreads, as I sell more and more putty, I need to scale my business, because when I started my business, I was just planning on selling to my class. But now word's getting out to my class, to my school, to like the whole community. And then that's like going to like the whole state of Washington. And then that's like going like West Coast. This is all just spreading. Like Mrs. C's putty is amazing. It's so wonderful. And then like soon everyone in the country wants my putty. So me making putty in my kitchen is not going to work anymore. I need to scale my business, which means I need to multiply my production. I need to multiply my whole business plan by a lot. Maybe by like, I don't know, maybe I have 1 million customers. So when you hear about scaling a company, it means getting your company ready to like go country wide or worldwide, because I just started in my class and that was fine. But as I got more and more customers, I need to scale my company, meaning I have to multiply my production by something, depending on how many customers I have, maybe by 1,000 or maybe by 1 million, so that I can give the people what they want, and the people want putty. Am I right? So when you see this word scale, just understand that that word means, what are we multiplying by? Okay? Scaling, and think of it, I like to connect it to a business model, because you hear scale your company a lot in like entrepreneur. I like Shark Tank. You'll hear them say, I need this money because I need to scale my business. Because I was just selling to my class, now I'm selling to the world. Cool. And so what we're doing in this lesson, you guys, is just thinking about like what happens to numbers when you multiply them by different scales, when you multiply them by a fraction or by a whole number or whatever. We're just thinking about what happens to numbers when we multiply them by different amounts. Cool. So here, fill in the blank with a numerator or denominator to make the number sentence true. So 7 times something over 4 is less than 7. Well, here's what I know. I know that 7 times 1 is going to be equal to 7. I know 7 times 2 is going to be equal to something more than 7. So if I want to decrease 7, essentially what we're doing here, you guys, is we're finding a fraction of 7. Well, 7 times 1/4 is going to be less than 7 because you're finding a fraction of 7. 7 times 1/4 is going to be 7/4. 7 times 1 up top is 7, and then we have a denominator of 4. 7/4 is equal to 1 3/4. And 1 3/4 is definitely less than 7. Okay, cool. So here, when we multiply a whole number by a fraction that's less than 1, the result is going to be less than our original. So the scaling factor here shows us when you multiply something by a fraction, and you guys already know this, it's going to have a product that is less than the original. Okay, sweet. So here, 7 over something times 15 is going to be greater than 15. So 7 times 15, how can we make that larger than 15? Well, in order to make that larger than 15, this is going to have to be, let's look at like 7, let's look at 7 halves. If I were just to find a fraction of something less than, I don't know, like 1/2 of 15, that's not going to be larger than 15. In order to create this side, the left side, in order to create a value that's going to be greater than 15, we need to find a fraction that's greater than 1. So let's look at this. So 7 times 15 up top. Let's see if this works over 2. What does that equal to? Well, 7 times 15, I don't know that off the top of my head. Just going to do some casual multiplication. 7 times 5 is 35. 7 times 1 is 1. Cool. So we have 105 halves. That is definitely larger than 15. The scaling factor here is an improper fraction. When you multiply a whole number by an improper fraction, the result is going to be something greater than that original number. Okay, very good. So you guys, this really is just an investigation into scaling factors, as you can see. Okay, so here we want to multiply 3 by something that is going to result in 3. Well, I know anything times 1 is not going to change the value of number. So what can I multiply? What fraction can I multiply 3 by so that our result is 3? Well, just a fancy version of 1. A fancy version of 1 is 5 over 5. 5 over 5 and 1 are the same thing. When I multiply 3 by a version of 1, we're going to get 3. Let's just make sure that that is the case and look at that. So we're looking at 3. We're proposing 3 times 5/5, which is equal to 3 times 5 is 15. Our denominator is 5. 15 divided by 5 is 3. Sweet. So that totally works out. Okay, this is a really important problem here. This problem involves, who would mind if I use them for this problem? Miley. Miley, thanks for letting me use your name. So Miley says multiplication always makes numbers bigger. Explain to her why this isn't true. Give more than one example to help her understand. Okay, so Miley is temporarily mistaken, and she's saying multiplication always makes the numbers bigger because she says, hey, well, if I multiply 1 by 2, my final product is going to be 2. If I multiply 1 by 3, my resulting product is going to be 3. And look, 2 is bigger than 1, and 3 is bigger than 1. Yes, that totally works, but what if we multiply what happens when we multiply by a fraction? Uh-oh. I think this does not work. Well, I mean, it works, but this is a case where multiplication doesn't always make things bigger. 1 times 1 is 1, and we have 2 as the denominator. So our resulting product is actually less than our original number. So yes, Miley, multiplication makes things bigger as long as whatever you're multiplying, as long as you're multiplying by a whole number. Once you start multiplying by a fraction, you guys know this. Miley, you also know this. Thanks for letting me use your name. When you're finding a fraction of something, that something is going to get smaller. Cool? Great.
Alright, 5th graders. Oh, that's interesting. Okay. 1/2 times 5/5. So we can all do this, I think, by now, hopefully. You've learned enough to be able to do simple multiplication. So on top we're doing 1 times 5, and then on the bottom we're doing 2 times 5. And then 1 times 5 we should know is 5. And then 2 times 5 we should know is 10. Sorry, I'm doing a really bad job of writing. And then we can also have this be 1/2, which is fun. And then B. Okay, just a second. Okay, now I think I'll just leave it. I'm going to do another problem. Just a second. What? Come on. Come on. What?
The orange looks really bad.
Oh, yeah, it does. Okay, now 1/2 times 3/5. Again, we can all hopefully do this by now. I mean, we should be able to. Now we're doing 3, 10. Because 1 times 3 is 3, and then 2 times 5 is 10. So we get 3 tenths.
Okay, why don't you clear it so it's easier?
I'm just gonna do, obviously, I'm just gonna complete the problem. Doing it as small as I can. This 1/2 times 9/5. Okay, we know how to do this, of course. Yay, got the easiest problems ever. Woohoo! Okay.
That was awesome. Thank you so much for doing those problems. I just wanted to do a little debrief. So you guys just saw 3 problems where Kira was multiplying a fraction by a fraction. So the scaling factor was a fraction, but the original number was a fraction. So when you're finding a fraction of a fraction, what is our result? The result when you're finding a fraction of a fraction, like a fraction, say this is a circle, but say we're only talking about like half of the circle, and I want a fraction of my half circle, we're talking about teeny tiny numbers, like a CSB schedule, teeny tiny. Fractions of fractions, when your scaling factor is a fraction and your original number is a fraction, the result is a teeny tiny number.
Okay, so first we're going to read the problem, and then we will start doing it. Okay, at the book fair, Vald, okay, I don't like this Vald guy too much. Yeah, I'm going to change it to Dylan, because he's a nice kid. Sorry about that. Dylan spends all of his money on new books. Pamela, I don't like this Pamela kid either. She doesn't sound Pamela. Yeah, I don't even know her brother's name. Yeah, I know. So I'm going to put it as Olivia, because that's Kira's friend.
She's my best friend. She's awesome.
We have 2 Olivias, so I'm going to do Olivia K. Yeah, okay. Oh my gosh, so neat. Olivia. It's not working that bad. Okay. Oh my gosh.
It's really hard to write.
Yeah, especially on the top.
Yeah.
Okay. As much as
Vol, just write a
okay.
D instead of Dylan.
Okay, I'm just gonna write D short for Dylan. And Ellie, I don't like Ellie either. I'm gonna put
She's just like
Millen. I don't, because that's my name. I like that.
Millen, Olivia K, and Dylan went shopping for books.
Okay, Now let's read the better problem. At the book fair, Dylan spends all of his money on new books. Olivia K spends 2/3 as much as Dylan. Millen spends 4/3 as much as Dylan. Who spent the most and who spent the least? Now, we have to start by drawing tape diagrams. The first one is going to represent Dylan. It's going to be D. The next one.
No, don't put them in the white crate.
Oops, 1 second. Okay, so Dylan, I think, should be equal to 1. Okay, and then there's Olivia K, who spends 2/3 as much as Dylan, okay? 2/3 as much as Dylan. So it should only be 2/3 as Dylan's. So first, to make this easy, we're going to split Dylan's tape diagram into thirds. So then we can do this into thirds. So this, just pretend my handwriting is bad. I'm actually just going to make this just to make it. No, you know what? Sorry. This is really not going how I thought. I thought this would be a lot easier. But I'm going to try until I succeed.
It's not backing.
Okay. So this is equal to 2/3. This is going to be 1/3. And this will be 1/3. Oops, wait, I forgot to do this. 1/3. 1/3. 1/3. Whatever. Sorry about my handwriting. And this is Olivia. So I'm putting an O. And then here's where I come in. Millen. So I'm going to put N for short. Now, this is 4/3 as much as Dylan. Crazy, right? 4/3 as much. That means I spent a lot of money. Yeah, I love spending my money. Sorry, this is not as neat as I would expect. I will next time do a lot neater of a work. Oh my gosh. This is getting really neat. Okay. So this is supposed to be 4/3. Sorry about how diagonal this is. It makes me kind of mad to think about how diagonal my work is. Okay. So each of these will be 1/3. Third. Okay. Now, as you can see, together, Millen spent 4/3. Olivia spent 2/3. And Dylan, he spent 3/3. So that means, what's the biggest? The biggest is what I spent. So that means Millen spent the most money. And now we have to do who spent the least amount of money. Well, what's bigger, 3/3 or 2/3? All of us would know it's 2/3. You're right. That means Olivia. I feel like I really spelled Olivia's name wrong. I did spell Olivia's name wrong. I feel so bad now. Olivia spent the least amount of money. Least amount of money.